Okay, hello everyone. Thank you for joining our monthly webinar organized by IEEE's Instrumentation Future Technologies Committee. Today's speaker is Dr. Nereida Rodriguez-Alvarez. Her presentation will focus on the full polarimetric GNSS-Reflectometry capabilities of the SMAP dataset. She will introduce SMAP dataset to the scientific community and highlight the main sensitivities of full polarimetric GNSS-R measurements to the Earth's geophysical parameters and the potential applications enabled by upcoming polarimetric missions. Nereida Rodriguez-Alvarez is a research scientist at the JPL Jet Propulsion Laboratory. She received her bachelor's and master's degree in telecommunications and PhD degree in remote sensing from Universitat Politécnica de Catalunya, Barcelona, Spain in 2005, 2007, and 2011. She has multiple awards. I want to highlight in particular her award in 2019 for the NASA Early Career Public Achievement Medal for analysis of BiSAC radar signals, as well as 2021, the Charles Elachi Award for outstanding contributions and exceptional ability in using BiSAC radar as an innovative tool for studying Earth's geophysical processes. So we ask that you please wait until the end of the presentation to answer questions, but please feel free to put your hand or question in the chat or Q&A box at that time. And with that, we look forward to your talk. Please take it away, Dr. Nereida Rodriguez-Alvarez.
Hello, everyone. I hope you can hear me. So thanks so much, for the introduction. I'm very excited to be here today and be able to share with you the ins and outs of the SMAP reflectometer dataset and more in general terms, the technological capability of full polarimetric GNSS reflectometry. So I'm going to start now. Let's see what happened here. Okay. Very quickly, this is the presentation structure. I will describe polarimetric GNSS-R measurements. I will provide information to understanding the SMAP-R dataset. Then I will show the dataset and how to get there, access it, and what's inside. I will then talk about how SMAP-R data can help, and then I will show few example investigations that have been done mostly by my team, but truly hoping that this will inspire some of you to take on and continue to investigate uses of this data set. So let's start with the basics, which is polarimetric GNSS measurements. So the next about 5 slides provide a bit of theoretical background. So thanks to missions like TechDemosat, Cygnus, and many others, we are very used to explain what the effects of the roughness, for example, are, especially over the ocean, as it provides a direct link to ocean wind speeds, right? So in terms of normalized static radar cross-section over the ocean, or in terms of reflectivity over land or sea ice, we generally understand that smooth surfaces are linked to specular reflections and provide higher reflectivity. For very rough surfaces, most of the energy is scattered off specular, and therefore the reflectivity goes down. Right? So I guess the question is what happens to the polarization of the wave as it reflects from different types of surfaces. For smooth surfaces acting as specular reflectors, as mirrors, as you can see in the pictures here, if we assume a transmitter at right-hand circular polarization, the wave will preserve circular polarization, but it will cause a phase shift that will flip it into the left hand. But the specularity dominates, and therefore there will be no depolarization effects, and therefore there is not much polarization information on this type of surfaces. Then there is the medium rough surface. A medium rough surface introduces small-scale variations in the reflection surface. The roughness will cause depolarization as the waves will be scattered in multiple directions. So what is expected is that if there is an incident wave at right-hand circular polarization, the resulting wave will show a mix of left, right, and some linear components. This therefore translates into the presence of non-specular components, and then therefore the energy is coming at angular directions other than the specular direction. We go to the other extreme. A very rough surface provides a wide spread of the scattered wave to many directions. In this case, what we will have is significant depolarization as the roughness disrupts the phase of coherence. which produces that the scatter wave show a random polarization state. In this case, circular polarization right and left are diminished in pro of the linear polarizations. This, of course, causes much reduced specular reflection, so less energy on that direction, but still there is energy coming from there. So this table now here that I put at the beginning includes a column for polarization state. And this is summarizing what I just described. So we can grasp the idea that polarimetric GNSS-R measurements are an asset to rough surfaces, especially, and especially full polarimetric configurations in which a pair of linear antennas are used. So let's talk now about measurement configurations. So the most common GNSS-R missions, what we have usually is a left-hand circular polarization antenna. And this is measuring the right-hand signal reflected or scattered from the Earth's surface. So basically, these antennas measure the component of the right-hand circular polarization wave that is turned into a left-hand circular polarization wave. So this configuration, as I said before, has no polarimetric information. Basically, there is no measurement on how this wave is depolarizing. So if we want to add polarimetric measurements to the standard configuration, the most obvious approach is to add a right-hand circular polarization antenna to see what part of the wave depolarize, or what part of the depolarization of this wave that is caused by the rough surface lay on the right instead of the left circular polarization antenna. The main problem with this configuration is that it is unable to measure the whole scattering distribution that also goes into linear polarizations. Also, a limitation is the low reflectivity of those signals, which impose requirements then on the technology, which is that the gain of those antennas needs to be better to be able to capture most of the, you see, for example, in this picture, the areas that go kind of black because they have very low reflectivity capture. Okay, so the other solution is to add a pair of linear orthogonal antennas. In this way, full polarimetry is enabled because the data from those linear antennas enables also to reconstruct the left and the right measurements. So additional to that, the antenna requirements on terms of gain of those missions that will be able to capture these signals is not so critical. So as a summary, I just want to make this note here, and that these maps the maps that I'm showing are not simulation or model signals. Those are actual measurements from the SMAP-R reflectometer. And this is kind of a summary of what I just said. So a single polarization configuration measurement will enable the green box measurements here. Then a dual pole configuration measurement will enable the purple box, which is these two on the top. And then a full polarization configuration measurement will enable all of them, actually. And I'll get to how we do that in a second. But this brings us to the missions and the data availability. So I have divided into these kind of categories, right? Like single, dual, and full polarization, and see what missions are up there. So this slide shows the different missions. We have TDS-1 that is no longer operational. Then we have Cygnus. We have Aspire with the near nadir measurements, and many other under this single polarization category. Then we have been seeing appear some other missions that are starting to add another antenna, which is usually right-handed. So then we have Aspire with the grazing angle measurements that can be combined with a near nadir, so we will have left and right. And then we have Mune, MUSAT2, that is also bringing dual antennas. And then we have the upcoming HydroGNSS, which is also gonna add a right-hand circularized polarization antenna to the mix. And then on the stream over there, we have SMAP, which is currently the only one that is providing full polarization measurements through its linear antennas. Has a pair of orthogonal antennas and is capturing that. So obviously this talk is about the SMAP reflectometer, so I'm gonna focus there. So let me introduce it to you and the story behind it. So the soil moisture active passive mission was designed with an L radiometer and an L-band radar, with the main purpose of providing soil moisture and first state estimation and aiming to use the radar signal to downscale the radiometer signal and provide higher resolution soil moisture at the 3-day revisit. Unfortunately, the radar suffered an anomaly on the transmitter about 2 months in, and the radar could not provide the expected data. So what the SMAP mission did was to switch the receiver band pass filter frequency to the GPS L2 band, which was within its technological capabilities. And from that moment, the SMAP-R radar receiver started to capture the reflections of the GPS constellation, turning therefore into what we have been calling the SMAP reflectometer or SMAP-R. And this is indeed the first space-borne full polarimetric GNSS reflectometer. Okay, so now I'm going to move into the data a little bit. So let's dig a little deeper there. Well, let me present the team. So yes, I wanted to make a point, stop here and just show the faces of the whole people contributing to this. So while initial efforts were made to process the radar receiver IQ signal into phase and quadrature signal into the delayed Doppler maps, back in 2020, we put together a team and a proposal that we were lucky to get funded these days, and we bring this dataset into a calibrated L1B dataset that could be used by the science community. While I was PI for the effort, it really took a strong team to understand how to process the raw data and what was really what we could see through it. The team is expanding thanks to the continued support of the SMAP mission, to which we are very grateful, and we are trying to keep this dataset production, deliver, and further investigation alive. So bear with me while I share some of the details on the processor and the signal processing. Here, what we are showing is the basic processing. We have done it rigorously to obtain a quality signal, while the processor does a very basic processing, like predicting when the SMAP rotating antenna will capture a GPS reflection, therefore cutting those IQ transects and cross-correlating with the PRN signals. We also added a navigation bit phase correction for the GPS L2C signal. And this is shown in that plot over here, this matrix of plots. This one shows the first one is the coherent integration without correcting for the navigation bit, and then the consequent incoherent integration in the second row, again, without correcting. So basically, this plot over here is the incoherent result of adding these two, this one, these three, this one, these four, and so on. So let me move this here. Okay. So then this line over here, it does the correction bit. It corrects for the bit phase, sorry. And then what you can see here is when we incoherently average those DDMs that were corrected, we get a lot more signals. So we went from 16.8 16 dB, let's say, to 23 dB. So this is about 7 dB more just for doing that. So as I mentioned, we wanted to make sure that we obtain the maximum quality signal possible before delivering. So this took a little bit of work. So what now? So now what I have here is a DDM that corresponds to the measurements of right-hand circular polarization signals measured with a linear H horizontal polarization, and the same measured with a linear V polarization antenna. So what's that? This took a bit of, sitting, reading, learning. It was a process, mainly to get ourselves out of the standard, where I have the expected DDM, and then I just plot the peak versus some geophysical parameters, and we do ratios between polarizations and so on. So we wanted to understand what we were really measuring here. So after looking into the radar field, we understood the signal, and we adopted the conventional way to express polarimetry through through the Stokes parameters. The idea is that any scatter wave can be decomposed into a frame of reference in which this frame of reference are the Stokes parameters. At any point on that sphere that you see there can be defined, of course, by the radius, which is obtained as the square root of each Stokes parameter, or in another way to express it, it corresponds to the intensity, which is the first Stokes parameter, multiplied by the degree of polarization. So this I times P here equals then to the square root of the S1 square, S2 square plus S3 square. And then this point over here also needs the definition of these two angles, for example. So the idea is that any point in the sphere can then be expressed by the Stokes parameters or by this type, the radius and the angles. So those are the Stokes parameters. Those are the Charles-Stokes parameters. Okay, so next, what we did is to compute the Stokes parameters following the mathematical formulation that you can see here, where in these formulas, the X and the Y represent a pair of orthogonal antennas. In the case of a SMAP, those are coinciding with H and B linear polarizations. So by computing the Stokes parameters, we obtain a complete reconstruction of the polarimetric scene. So our products are in terms of the Stokes parameters, but we also we also produce the bistatic radar cross-section, reflectivity, and things like that. Okay. Also note that the signals have been calibrated. We have accounted for many parameters or many effects, which are the transmitter signal axial ratio and phase offset of a perfect circular wave, two-way Faraday rotation from transmitter to specular point and from specular point to receiver. We also account for polarization misalignment, or in other words, the fact that linear antennas are not aligned with H and V perfectly. In this case, for us, because this is a SMAP and it was the design of a radar, it is very good aligned. So in our case, it's minimal, it's only 0.5 degrees. But any other pair of linear antennas will have to correct for that. We also account for receiver issues, such as the antenna pattern difference between the X and Y polarization, H and B, the receiver offset, and the antenna cross polarization component as well. So you can find much more information about that in this publication over here by my colleague, Juan Fran Muñoz Martin. Then the following slides just want to show an example on how the Stokes parameter DDMs are computed and how those actually look, right? So this one here is the first Stokes parameter, or the intensity, also known as, you know, in this plot over here, it was this capital I over here. So we use the first Stokes parameter for normalization of the other three. As you can see, it corresponds to the total energy received by adding the energy received in each channel. And it is also equivalent to the sum between the two circular polarizations. So it is the total energy of the two orthogonal polarizations in this case. So just remember that. And then this is something, therefore, if we can, since this is equivalent, this is something that we can measure both with the dual and the full polarization emissions. So we'll have S0 over the first step. The second Stokes parameter is computed as the difference between the two channels, linear channels. And so here is an example DDM. Doesn't look very good, but when you plot it over the Earth, it looks much better. And also, you can see towards the right here, how this second Stokes parameter look over the land and over the sea ice. You can see just from those two simple examples that there is correlation between this second Stokes parameter and, for example, geophysical information, in this case for the top one, which is over land. You can see that it correlates with the vegetation water content. So like in the deserts, it has this value, but over the forest, and so it has different value. So it correlates a lot with the vegetation distribution. For the sea ice, it clearly shows two signatures. Like you can see, this is January to March. So this part over here is ice, and there is a clear boundary here where this is the no ice or ocean. So we will dig deeper into this towards the investigation sections later on, but the point that I want to make is that this can only be measured by the full polarization missions, not a dual. Okay. So same for the third stock parameter. This is computed as the real part of the cross correlation between channels, which is also equivalent to the difference at the 45 degrees angle of the polarization, of the wave. So the images over the land and the sea ice show variations with geophysical properties too, as you can see. And again, this one, since it's coming from the cross correlation of these two linear channels, can only be measured by full polarization missions. Finally, the four stocks parameter. This is computed as the imaginary part of the cross correlation between channels, but is also equivalent to the difference between the two circular polarizations. Therefore, this is something that we can get with both dual and full polarization missions. And it also, you can see that it has a lot of sensitivity to sea ice and to the land as well. Okay, as I mentioned, we can also compute normalized bistatic radar cross-section. So we follow the standard approach in which the received power is, in this case for us, is the total intensity, is this first stock parameter. And we just, as you know, in order to compute so I mean, that's a DDM. So we have this distribution at a certain delay and Doppler, and then we can get this and we can divide it by the scattering area, therefore obtaining the normalized static radar cross-section. What we can also do, and we did in order to compare to Cygnus, is we substituted this use of the first stock parameter to compute the received power. We computed the equivalent in the right left, and then we computed this scattering, the scattering cross-section, the normalized scattering bistatic radar cross-section, and then we compared to Cygnus. And we collocated, of course, the data, and you can see that the bias is about minus 0.25 dB and RMSE of 3.3 dB, which is well within the, the errors that other missions also observe as compared to Cygnus. Okay. So this is a map of normalized bistatic radar cross-section over the ocean, just to show you how it looks. And I believe this map, it covers from June to November 2019. Then here we show how reflectivity is computed from the bistatic radar cross-section by taking a box of few delays and Dopplers, which actually is equivalent to the SMAP antenna footprint. So we integrate that and correct the incoherent computation to the coherent standard formula. And this is how the reflectivity looks over the land and then over the sea ice. So we can also have these standard measurements. Then bear with me. Now I'm going to go through the stocks parameters, which are in this sphere here, the different angles that we can see and the radius. So this represents an alternative way to describe the depolarization. So if you look into the sphere, as I say, you can follow what I'm talking about. This one here is the degree of polarization, or P, and is computed using the Euclidean norm of the second, third, and fourth stocks parameters divided by the intensity over the first stock parameter. And this is how it looks over the ocean, over the ice, and over the land. For land, for example, it seems to be a good description of volume scattering, and it does correlate with BOD. Then is delta angle, which represents the phase difference between the two linear vectors of the scatter field and is computed as the arctangent between the third and the fourth stocks parameters. So I did not put it here because it was difficult, but in this plot. But think of it as when we have this delta angle equal to minus 90 degrees, that means that the H and the V components of the received signal are out of phase by 90 degrees. Hence, the signal polarization is perfectly left circular. Delta, as you can see, provides clues in different penetrations in the surface for different polarizations. You can see it maybe here over the sea ice. It has a lot of variation. Sorry, this keeps moving. Sorry. Yeah, I was here. Yeah. For land, for example, it seems a very good description. Seems to provide information also quite relevant, but which is very distinctive here for Delta, is this signature over Greenland. Then we have chi, that represents the ellipticity angle of the received wave. So an ellipticity of minus 45 degrees means that the signal has both H and V axes equal, therefore that the signal is circular. Whilst for an ellipticity of 0, the received signal would be completely linear. So you can see also variations over the landscapes for this one. And then we have C. C describes the polarization angle, or also the orientation of the wave. This parameter is directly related to the axis of the linear component of the reflection. So you can see also the variation. It seems less over land, it's less sensitive, but it has very good distinction over the forested areas as well in Greenland, as you can see. Also over sea ice, it provides a very nice boundary between the ice and the no ice. But then over the ice, it doesn't have a lot of variation. Okay, I think that's maybe enough about this. And now we can go into the SMAP-R data availability. So the SMAP-R dataset was released after a long process of validation through peer review publications, and then dataset and metadata reviews by subject matter experts. So you can simply now, if you want, you can Google SMAP-R L1B, and it should bring you to the new data release notice from the NSIDC, which is this here, and it has some links. Or maybe it will bring you directly to the landing page. At least when I put it in Google, this is what the first two links that I get. This is the citation. So of course, you can also access this data set by going into the DOI over here, and it will bring you directly to the landing page, which is this one over here. So that's okay. So I don't know if you're following, but if you are doing it, once you are here in this landing page, you can just let's see, scroll down, and you will find this area over here for data access and tools. Oh my gosh, this thing. And then you will also see a section for documentation. So under documentation, we put a few relevant literature to enable the scientific community to understand the data set. So all what I have said is published in all of these links over here. But if we go back to the data access over here, we can just click on this HTTPS file system. And what this will do is it will take you to this probably, which is their data login page. You can log in if you have a user, or you can register. That's fine. But once you do that and you log in, you will see the NSIDC, which is the National Snow and Ice Data Center repository. From there, you can download with standard bash programs, or also you can go by one, which I don't recommend because this data goes back to 2015, so there is a lot of files in here. So you can just build a bash file, a bash program to download this recursively. And then once, let's see, we can just click on one. If you click on one, it will just download directly to your computer. So once you have it, I would suggest that you open some type of software, I'm sure most of you have it. If not, I recommend Panoply, which is a very good interface that helps navigating the data set. So once you have the Panoply open, you can just drop in the file that you just download, then C file, it's a netcdf, and you will see the different variables. So what we've done is we have tried to make it as comparable. Sorry, I'm gonna drink. To make it as comparable as Cygnus as possible. So the naming that we choose is very straightforward, and if you are used to GNSS-R datasets, it shouldn't be so difficult to get used to it. Also, each variable has associated metadata explaining what it is and the dimensions. For example, let's take one, which is the bistatic radar cross-section, and is this BRCS, and you can see the metadata associated to it. The DDMs, for example, it says here is 7 delays, 100 Dopplers. And then this is both geolocated in lat long, and then it is time tagged. So time lat long for each individual DDM. Okay. So you have the data now. So how can SMAP-R data help? One of the things that can be done with SMAP-R data is to reconstruct signals into different polarimetric configurations, as I was mentioning. And this what can allow the community is to better understand what other missions will see, especially the ones that are being built or the ones that can be designed. So this is a very good tool just to play with the data, IQ data, and see what it can be done and can be seen, and what is this signal going to be sensitive to. So we are here, as I was mentioning at the beginning, and now following here, we reconstructed the reflectivity in the different polarizations, trying to guide what the antenna gain requirements were. Then another thing that we did as a request from the SMAP mission is we help during antenna pointing error efforts. The idea is that the specular point, the azimuth angle of the specular point is almost aligned with the SMAP antenna azimuth angle, but not with the elevation angle. It has like a range of plus minus 2.5 degrees of the actual, and then we can play with that to see where is the antenna really pointing to. So we basically found that there was a noticeable error in elevation angle with respect also with season, ascending, descending, and view angle. So the average of all of these variations that you can see here is minus 0.22 degrees respect to the pointing of the SMAP antenna. So in azimuth, as I said, it was negligible, 0.03 degrees, but the error in elevation, it translates into a geolocation of 2 kilometers and between 2 and 4 kilometers. So we did that. So this, it was an unexpected use of the SMAP-R data. But SMAP-R data can also help improve models. We have almost 10 years of data and more than 10 million reflections in very diverse Earth surface conditions. We capture seasonality, we can investigate trends, and it even can enable to produce some science for geophysical variables with very low dynamics. So let's see, let's run through some of the example or sample investigations that we have done and see if this can inspire you guys to keep on working with this data set. So we conducted the studies on seasonality. For example, this is just the reflectivity maps whose variations we looked seasonally, right? Like every 3 months, right? And we compare among them. For example, this one in the middle is July, September to January, March. And we have this soil moisture map. So you can see like this over here, which is variations in soil moisture, are also observed over the reflectivity map that we are producing. Also, looking into sea ice, as I have been mentioning, we observe the seasonality of the stocks parameters. So this is in January, March, then we have it in August, October, we do the difference, and you can see how these are not the same. Therefore, there is some seasonality attached to it. Then also we did the same study with the child stocks parameters. We also observe the whole seasonality. We also look into seasonality of three states over the cryosphere. So here you can see January to March, June to August. You can see those are different. We went a little bit further and tried to produce these maps at a monthly pace to see if we could observe the transitional phases between, thaw and frozen states. And for that, we use both the reflectivity, the stocks parameters, the child stocks parameters, and so. Then another thing is that we also conducted low dynamic variables analysis, such as the overall roughness of the land surface. Of course, agricultural zones, that's different, but overall roughness we can do with the SMAP-R. We were able to investigate different scattering assumptions at the microwave road mean square height, and then also topographic scale through DEM's slopes. We also did some sensitivity analysis. For example, using the polarimetric ratio approximation, we compare the SMAP-R measurements to the BOD as the function of the soil moisture, as you can see in these plots under here. Okay. So we wanted to see the trade between low soil moisture and high sensitivity to BOD, to when we go to the other extreme, and we saw that we have high soil moisture, and these triggers a loss in BOD sensitivity, but not completely, as you will see. Then we took SMAP-R computations of the reflectivity V and H and used it to I didn't flip the slide, sorry. And use it to downscale the SMAP radiometer measurement. So this first plot over here is the soil moisture at the original TB. This is the product that the SMAP mission produces. It's an enhanced product, but they are using a Bacchus Gilbert to recreate it at 9 kilometers, but the resolution still is 36 kilometers. And then we try to downscale this guy using SMAP-R reflectivity information, as you can see in this formula over here. And as you can see, it has so much more detail, as we can see all the rivers and different features in the land. Then we've been the data and observed that when the BOD increased, like here in this plot, when the BOD increased, we were observing a bigger or a bigger difference between this soil moisture product and our soil moisture product. So now the question is that good or bad? So are we introducing error or reducing it? So we basically want to look into that. We selected sites with considerable BOD from the Calval sites from SMAP and observed that actually the RMSE improved in all of them when using the SMAP reflectometer interpolation, kind of. Which means that when BOD is higher, downscaling the TBs with SMAP-R actually help to obtain more accurate soil moisture measurements. We also did sensitivity analysis of the SMAP-R data towards sea ice concentration, and after that we also look into the thickness. Here is an example of the two correlation matrices for both applications. For SIC, we saw that the ellipticity and the second stroke parameter were good descriptors, while for CI thickness, sorry, we saw that the reflectivity, the degree of polarization, and the fourth stroke parameter were more sensitive, that's very good because the fourth stroke parameter, sorry, what is it here, is something that missions like hydrogenesis will also be able to measure. So then we develop, and I'll give full acknowledge here, a not very sophisticated neural network, and we try to do like a quick retrieval to check on what could the performance be. So in this case, in this slide, I'm comparing to the NSIDC data on extent, and we did this neural network, and we got a correlation of 84% and an RMSE of 0.27, which is not bad. Then we also did the same with NSIDC data on sea ice concentration. We got a correlation of 89% with an RMSE of 0.20. And then we also tried to look into the sea ice thickness. So in this particular case, we use SMOS cryosat data, and we got a correlation of 70% with an RMSE of 0.49 meters. So this can be done better. We actually have a follow-on project that is looking into sea ice much more carefully. So another amazing discovery too, in my humble opinion, is Greenland. So we plotted the different stocks and child stocks parameters and saw that it revealed two different signatures. So the top maps are reference maps for ice sheet thickness and bed topography from the Ice Bridge bed machine. And our signatures show, as I was saying, these two types of behavior. So we have some of the parameters showing this type of behavior. And then we have some others that show this kind of, deep in the middle of Greenland. And sorry. And we don't know really what it is yet. We are looking into it and trying to figure out how these signatures correlate to Greenland's main features. So if anyone has ideas, they are very welcome or want to work on this. The data is available. So as an initial test, we look for ice sheet thickness from that bed machine dataset and look into the sensitivities of the stocks parameters. So from the sensitivity matrix, it looks like delta here, and the third delta and the third stock parameter could be good description in general, but when looking into the profiles, right, for example, delta and the ellipticity chi, which is this other one, we can see, just to depict how this looks versus these two type of shapes, right? So it looks like chi shows something somewhat expected, which is the dependency that chi is this one over here, that saturates at some point. The only thing that may pose some question is this seems to saturate like a 1.6 kilometer thickness, which is a lot. And then for the delta, it shows a similar dependency right until this it hits this middle here, and then it goes down back again. But also the kind of the thickness is also 1.6 kilometers. So I don't have all the answers, but those could be investigations that would be very interesting. Okay, so moving on, we also look into the sensitivity of SMAP-R to freeze thaw state. Here, what we did, sorry, my computer is trying to update something. Sorry, hope you guys don't see it. Okay. Yeah, so we did a comparison, as I was saying, between the SMAP freeze-thaw product and the SMAP-R product that we generated. There is a paper on the algorithm and so. So then, of course, we did the difference between the two products. And as you can see, it's almost zero, which means that What this means only is that we were able to perform at least as good as the SMAP-R radiometer, which in itself has an accuracy of 80%. But of course, our target output was the SMAP, Fristo product. So this table here shows a little bit of the performance of this study per year. You can see that it works pretty well. Most of the confusion is around 5%, and it originates from few occasions when the target is frozen according to the official product, and then the SMAP-R algorithm classifies it as thaw. Other than that, this algorithm seems to work pretty well and can be extended to other mission data as well. So let's see. So as I'm reaching the end of the presentation, so I wanted to leave you with this chart. So SMAP-R is unique and is transformative. It is the first ever space-borne full polarimetric GNSS-R dataset. We have nearly 10 years of continuous data collection, over 10 million reflections spanning diverse Earth surface conditions. Also, in addition, that I haven't mentioned, but it was was an implication there. Every sample of the SMAP-R dataset is collocated with a measurement of radiometer brightness temperature, and that can offer enhanced insights. So we hope and we know that the SMAP-R data can help you unlock new insights across Earth science. We have shown you it has value in many disciplines. Here, some more complete list if you want, like land and vegetation, soil moisture roughness, BOD, water systems, wetlands, floods, freeze-thaw states, transitions, cryosphere, sea ice salinity, density, and thickness, environmental monitoring, oil slicks, algal blooms, ocean roughness, ocean winds, etc., etc. So SMAP-R can really help your research. It can be combined with radiometers, with radars, optical data. It can help develop models by integrating multi-sensor data. It can be used for downscaling, low-resolution sensors, spatially speaking, or high-resolution sensors, temporally speaking. So more information on our SMAP-R work can be found here. Feel free to take a screenshot or a photo, or I can just email you that if you want to look into all the work that has been done and what else can be done, right? Then acknowledgements to NASA, the ROSES program, and the SMAP mission. Thank for their support on these investigations and all the research and all the dataset development. And that's it. Thank you so much for your time. I will be happy to answer any questions you may have if you are not, sleeping right now. So, yeah.
Wonderful. Thank you so much, Dr. Rodriguez-Alvarez, for your presentation. Everyone, just as a quick note, if the audience has any questions, we ask that you please put them into the chat or the Q&A box or raise your digital hand. While we wait for those questions to come in, let's start with one of the questions that we currently have in the chat. It asks, what is the spatial resolution of each measurement? Would it be affected by the special rotation feature of the SMAP antenna?
Yes. Let's see. So like in any GNSS-R mission, the spatial resolution of every individual sample depends on the landscape. So it can go from anything between, let's say, 1 kilometer, 3 kilometers over very smooth surfaces to 40 kilometers, etc., over vegetation or over ocean, etc. The SMAP-R antenna is actually filtering the DDM in those very, extreme cases where the spatial resolution is 40 kilometers. Therefore, the tops, what we are seeing maximum is 36 kilometers, which is the antenna beam pattern. Yeah. And then as for the rotation, that limits us in terms of, sampling of the surface. So we don't have a continuous measurement. We see it now, we see it after 4 seconds, etc., etc. What this provides is a very sparse data set that, so and therefore it has implications on the science, but it can be used as for models, etc., etc.
Great, thank you. We have another question. So why in the case of SMAP is the receiver antenna XY planes always aligned with the HV planes?
Because it was designed for the radar, and the radar was designed to be pointing exactly to the Earth scattering H and B. I can
Great. While
hear
we,
you.
yeah, great. While we wait for other questions, I have one myself. So, you showed several great sample investigation ideas, looking over land, water, cryosphere. To you, which shows the most promise, and which areas do you feel still need more improvement? And if so, what are your plans for that?
So the sea ice is very promising. Also, the coverage for SMAP-R is a bit better towards the top of the Earth. So sea ice is one. Freeze thaw, it's another one, but not for SMAP-R, but to get, inspired by SMAP-R for other missions like hydrogenesis or Aspire, etc., where they also have dual pole. And it's very useful still, the dual pole over those areas. So we have to, see what the technology is coming is dual pole. So let's see what we can do for those. And that seems to be a two potential very good applications in there. Soil moisture also very good, but it will depend on the revisit time of these new missions coming up, right? Because soil moisture usually is something that the science community wants at a higher temporal resolution than maybe 10 days or whatever. Yeah.
Yeah. We have another question in the chat. For how long do you think SMAP will be active?
Well, for now, what we can say is, I believe in the next 3 years it will, right? And then, yeah, I mean, it's already an extended phase. So, yeah.
Great. And so if it is extended, can you say more about what is next for SMAP-R?
Yeah. So if the radar cannot come back, which there has been some initiatives going there, if it cannot come back, we will continue to produce our data set. If the radar were to come back or was to come back, we will not be able to produce any more SMAP-R data because, of course, the radar will be doing something else. But while the radar continues in the current state, we will continue to produce. The SMAP mission is supporting this generation and this production and delivery. So it will continue to be there for as long as SMAP is alive. Yeah.
That's great. Let's see another question in the chat. You just mentioned that SMAP-R coverage is better on the top of the Earth, but GNSS has lower coverage in the poles. Does it exploit the grazing angle signals, or what did you mean by that? Thank you.
No, it's just that overall the chances that we have to, since this map is revisit over there is more like a 2-day, we just have more chances. But yeah, you're right that the pole is not well covered. So you can see in my maps, like, there is a hole in the middle of the sea ice that we cannot cover. Yeah.
Right. Let's see. I don't see any other questions. I have one more question. So I thought, oh, wait, one question just came in. Let me ask their question. So is SMAP also using GPS L5 signals that are higher bandwidth?
No, it's not. It's not because
Mm.
the the radar, it was closer to L2, so it was able to move there, but no, it cannot cover the other. Yeah.
Yeah. Okay, so my question, I thought it was fascinating that, you might have sensitivity to ice sheet thickness using SMAP-R. You were mentioning something about 1.6 kilometers. Is that where you're saying you might lose sensitivity? That's as far as you think it can go? Or what are your thoughts for improving ice thickness measurements, potentially using SMAP-R, or at least sensitivity to that?
Yeah, I mean, I am surprised even for the 1.6 kilometer. So I don't really know if this is, I mean, it seems to be the ice sheet thickness. I don't know how, I don't know what to say because I would expect less than that.
Right. Yeah, I was fascinated by that as well. So
Yeah.
it'll be interesting to see follow-on studies to that and what people come up with. Okay, one last question, and then I need to start getting ready for my class. But
I
does
know.
SMAP have sensitivity for snow parameters such as snow water equivalent?
I don't think so. I don't think so. We had an investigation over, so the snow over the sea ice, and we couldn't see much sensitivity to it. I don't know whether if it was because of the electric constant of the two, and maybe over soil it would be better, but I haven't seen anything so far that indicates so. Yeah.
Okay, well, great. Thank you so much for your time. I do not see any other questions, so I would like to close out the session by thanking you again, Dr. Rodriguez-Alvarez, and thank you everyone for joining us for our monthly webinar organized by IEEE's Instrumentation Future Technologies Committee. So thank you. Have a great day.
Thank you so much, everyone. Thank you.